Teams has decided to not respond on Tyler's computer, so I guess we'll take a couple minutes here to work on some technical difficulties.
I'll just say that I saw Tyler yesterday. He was looking beautiful. Appreciate that info, Caitlin. He was doing well, had a smile on his face. Not sure what's up with the new teams, but I can vouch for him. So, yeah.
Thanks, Jesse.
It's really all I've got. I'm pretty excited for his presentation.
I think a lot of us are. I know at KPFF that they got a whole watch party going, so it's exciting.
I see Robert's on. Maybe OCI is doing the same thing. Watch party.
And you could just share it and feel.
I could just share.
Or plug into the thing so it's up there too. But if he needs to point to stuff, that's gonna make it.
Do you have any jokes, Jesse? Nothing? Nothing from the kids?
This is a professional setting, Robert.
Not even a knock-knock joke. I think people would be fine with a knock-knock joke.
I was not prepared. I did need to check in with my...
You don't think you see me? Okay, I have a joke.
Oh,
How do mermaids wash their fins?
I don't know. How do mermaids wash their fins?
With Tide.
Oh my god.
Oh.
That was good.
That's a good one.
Bookmark that one. Welcome, Tyler.
Yeah, thanks.
Thank you, teams.
Yeah, thanks, teams. Perfect. Get it come early, get it set up, and you have problems. Can everyone see my title slide? Okay, perfect. Yeah. Thanks for the introduction, Caitlin. Yeah, so I'm going to talk about organic material in simulated stream bed design, flume study, investigating meander bar design and guidelines with organic material. This was conducted at Washington State University at Albrook Hydraulics Lab, and this was all funded under WashDOT. So a little overview is we're talking about a little introduction, reference stream, laboratory setup, data collection, our meander bar design, organic stream bed mixtures, and then we'll jump into our results. So in Washington State, the largest fish barrier is culverts. And why are they barriers? Well, because they're either figure on the left, they're either perched, so the downstream bottom culvert is above the water surface. So this surface difference can be too big for juvenile fish to make up inside the culvert, or adults can make the jump, but then maybe that velocity is too fast and the fish can't make it through our culvert, or they're undersized, as if two figures on the right. You see in the middle figure, that solution was, oh, we have a small one there, let's just add two more on the side to help with those flows, decrease that velocity, but then you have one becoming perched. So in Washington State, there are about 3,500 stream crossings. And of these 3,500, there's about 2,000 fish barrier culverts. Supreme Court decision in 2016, made a decision that 90% of these have to be replaced by 2030. The estimate cost is, $4+ billion. I think it's more around that $7 billion range now. So our design's expectation goal as meander bars is to develop a channel shape that's more natural in the system, and we want to see it become, a meandering stream to keep it off the entrained walls. So meander bars are made of coarse material that will maintain a target channel shape, and then the addition of organic material increased with meander bars will decrease sediment transport. Our next design is organic stream bed mixture. So mixing organic material into our stream bed mixture will increase channel stability. So our laboratory setup, we had used a reference reach of the Fouty Creek in the southeast corner of Washington State. The mean substrate, the D50, is 63 millimeters. We conducted a flood frequency analysis to scale our flows into the lab. So flood frequency analysis on the right is we try to keep our two flows between the Q5 and the Q95 to stay right in that range. So we can say we have a D1 or a flow of a 100-year flood event. We keep it between those two red values. So we can say that it's consistently there. So lab setup, you can see the bottom picture is looking into one section of the Albrook Hydraulics Lab in Washington State. On the back far corner, you see a 75-foot long tilting flume that's blue. It is 3 feet wide. So we had a 20-foot section of stream bed material. And in that 20 feet, we looked at the middle 10 feet of the study section to decrease boundary conditions. You can see the figure in our top right. Looking downstream, we have those vertical slats to create a back pressure effect so our sediment wouldn't wash out. So that boundary condition there will not impact our study section. We had the same setup upstream. So for the lab, we scaled to a Fouty Creek by using the D50. And so our scale factor is 7.6. And so that scales our flows in our lab. We could hit was 0.2 to 4.2 CFS. Scaling that in the field, we could hit a 2 to 1,000-year flood event. So to collect our data, we used a handheld 3D scanner. So doing this is we were able to collect about 4 million data points per scan, and it took us 3 minutes per scan. So you can see on our right is we have our pre-flood event scan, and then we scan after our flood events. In the top right is our post, and we can now subtract those two to see what the difference was in our surface bed. So you can see in the blue was erosion, and that yellow color is deposition. We can see where it's occurring with all this detail about how these features will change the bed of the channel. So here's a little video of a time lapse of the day in the lab. So we start off by stirring up the bed, then we just level it out. Then we dig in our desired channel shape. Here we're looking at deformable grade controls. So construct it, put it all together. And then once that's complete is we'll take a 3D scan of the stream bed, and then we hit it with a flow event. And so this flood event will go up, build up to a 10-year flood event, and then we'd maintain it for 20 minutes. After 20 minutes, we shut it down, let it drain, scan, then we increase that to a 25-year flood event, then go up to a 50-year flood event. And then we tear it all down, and then we repeat it for up to 3 trials, then we move on to our next design. So meander bars. So what are meander bars? And the figure on the right is meander bars that kind of wanted to mimic like a point bar. We want to be able to forcing a meander through our crossings. So we have this material at the head, looks like an ice cream cone cut in half. The head is made out of our D200 to 300 particle range. And then our cone, which is just downstream, is less than the D200, but greater than the D100. And then so this is our basic design throughout this study. So looking at meander bars, we had 4 designs. The first thing we want to do is, okay, how does this channel shape function with just using stream bed material? That's design 1. Design 2 is Now let's do that with made of coarse material. So using that D200 to 300 for the head and the D100 to 200 for our tail. Our third design was leaving that coarse material, but then adding a root wad built into our system that was buried inside our meander bar. And then design 4 is that coarse material with slash located just upstream. So we tested these designs at a 2, 3, and 4% slope. And for our 2% slope, we tested these at different spacings between our meander bar heads. So we used the flume width as our scale factor. So we call that culvert widths. So it's 1 to 3 culvert widths. But then looking at bank full width, that is 1.5 to 4.6 bank full widths spacing between these features. So figure left is our meander bar with a root wad, and you can see that's buried into our meander bar head. So we wanted to do this was to see if that log would be kicked out or not. So we used a scale down root wad to plywood and cut circles, stuck them together, and wrapped it with a burlap sack to really capture that weight. So we don't have the complexity. We wanted the weight of it to be mimicked. Design 4, figure on our right, is our slash material. You can see it's not incorporated in our meander bar head. It's just located just upstream, and it is buried at least half the length of these dowels. So here's a video we're going to jump into showing what actually the flow looks like going around meander bar at a bank full width. This video is taking at a 3% slope with our slash material. As you can see, it hits the head material and it kicks it to the opposite bank to make that meander. It goes down, hits the other one, and so actually making that meandering stream at a bank full event. So our results is looking at the stability of our channel. How much stability was increased by adding coarse material, root wad, or slash. So our 0 on this graph is showing that just using Streambed material. So we can see by adding these 3 designs that we increase stability in our channel. And we see that we add that organic material, we increase stability than just not having organics. We can see that our MBCMS is our slash. We can see that had an increase in stability for each flood event, with the blue being a 10-year, red is 25, and the orange is a 50-year flood event. So looking at our scans, so our on the top is our right after construction. This is our baseline scan with no flood events. And then the graphs on the bottom are after our 25-year flood event. We can see that looking at our Streambed material on the far left is baseline, and we can see that we lose that meander bar feature. So we can see that we had erosion along our banks, and we can see there's little deposition occurring in the center of the channel. And so this, over time, this channel is becoming flat and be plain bed. And just by adding coarse material, we can see that we maintain that meander bar shape, and then we have a little bit erosion on our banks with deposition in the center of the channel. And we can see this process occur for both our root wads and slash designs. So looking at where exactly is this erosion and deposition is occurring, we can look at the difference plots. So kind of outlined in white is kind of the location of our meander bars. And so we can see in blue is where our erosion is occurring, and then that yellow is deposition. And so we can see that we did see that erosion of our meander bar on the left bank, and then our deposition throughout this middle of the center of the channel. We can see by adding coarse material in our meander bar head, there's little to no change occurring around it. We do get a little erosion along the edges. That's due because particles just sloughing, not being totally packed in during construction. So we just kind of built these how you would in the field. We didn't want to make it perfectly, these are stays down, treat it like running an excavator or heavy equipment. They're just going to just dump these in there. They're not going to make sure they're completely packed. So we wanted to keep it more natural to how it would be constructed in the field. We do get an increase in erosion along the right banks on the class 2 designs. As due to that velocity is getting pushed to that edge of the channel, as we saw in our previous little video, as it hits the head and is kicking that velocities over to that left bank. So, coarse material reduces that erosion on the meander bar, but then the addition of organics, increased deposition in the center of the channel and that bank erosion on the left bank. So we're looking at a cross-sectional view as, okay, how does this channel profile change with just stream bed material and then our slash being our best design. So in the top figures are located at our 2500 cross-section. We can see here on the left is our stream bed material. You can see we have bank erosions on both sides and then deposition in the center of the channel. So the black line is our baseline. The blue is our 10-year event. Red is our 25, and that crayon is our 50-year. And you see how deposition in the center of the channel starts to increase further with the higher flood events and bank erosion. So over time, this channel will become plain bed. And then looking upstream, just adding the meander bars with coarse material and slash, we can see that there's, just a little change throughout our channel. We do have a little deposition or erosion occur in our center of our channel after our 10-year event, but even after a 25 and 50-year event, there's no little change after that initial flood event. Then looking downstream, we can kind of see the same process. We do see a little more deposition in the center of the channel for our coarse band with slash, but there's still very little change, and that it maintains our initial channel shape very well. So looking at the spacing of one culvert width, so we shrunk it back down. So this would be 1.5 bank full widths. We can see that we do see that same process where stability does increase with these designs over as having natural stream bed material. We do see that our slash material is the design has the most stability for our 10, 25, and 50-year flood event. So looking at our stream bed elevations, as we can see, once again, after our initial 25-year flood event for our stream bed material, we do start to see erosion occurring around our meander bars and deposition in the center of the channel. You can see that pink colored turning a little darker. And we do see this process throughout our channels over time. So kind of digging in to, okay, where's this deposition during an erosion occurring? We can look at these different plots to really understand, like, okay, how much is it changing? And we can see that by adding this coarse material and organics is we have very little change occurring around our meander bars and center of the channel. So we reduce erosion and reduce deposition in the center of the channel. For slash material, we do see a little increase in deposition right around this middle meander bar. What's going to be due to we had a little more erosion occur around our upstream meander bar. But given this little bit of everything else, is there's very little change. So it's maintaining our desired channel shape over these flood events. So looking at a cross-sectional view, we can see that with just our stream bed material is we have bank erosion along the side, and then we have deposition in the center of the channel. And by adding our designs is we see that we do have a little bit we have erosion of our bank here, but then it still maintains that same channel shape after a 50 to 25-year flood event. And looking downstream is we can see that we have a channel shape that pretty much stays constant. There's maybe a couple millimeters worth of change throughout the whole channel. So at a 2% slope, we looked at adding organic mixture into our stream bed. So this was done as a volume ratio. So we said we're mixing the whole stream bed up. So we looked at different ratios of how much organic material should be mixed into stream bed material. So we used 3 different stream bed or organic material. So we used broom corn, which is a very small diameter, like old school brooms. Ordered a bunch of that, cut it up. That was less than 2 inches in length. We used 1/8 dowels and then 1/4 inch dowels to represent our organic material. And so we looked at volume ratios of 3 parts organics to 1 part sediment, a 1-to-1 ratio, and then 1 part organic, 3 parts sediment. So we had super rich organics to very little organics. So looking at, what happens to our channel difference between each flood event. And we can see that, we do see erosion along our meander bars using organic material, and then deposition occurring throughout the channel. And this deposition is really just racking of this organic material that is getting caught up with the slash material above the surface. And we can see that we have a lot of that racking occurring for our increased in abundance of organic material. So looking at our surface profiles, we can see that, once again, that not having any features, just stream bed material, we have a plain bed stream forming that has become straight. But then adding organic material is, we can see we maintain that desired channel shape with erosion and deposition occurring throughout each of these designs. And we see that we have this rich organic, it's channel is very little defined because there's so much organic material inside this channel. So looking at our cross-sectional profiles, once again, we can see by looking at these 2 figures on the right that our channel shape is very well maintained throughout each flood event. By not having these designs, we can see that we have massive bank erosions and deposition in the center channel, leading to that channel to be plain bed over time. So shrinking down our spacing between our meander bars to a 1 culvert spacing, we can see that we have, little to no change for our organic mixtures for a 3-to-1 and a 1-to-1. We do see some of this material start to increase in erosion being moved at our 1-to-1 ratio, and we do see this racking on the opposite bank. Then once we get up into our very rich organic mixture, we see a lot of erosion and then massive racking of material in the channel. Looking at the surface difference plots or surface elevation, is we can see that the bottom graphs show our channel shape is being maintained. We do see an increase in our bed elevation for our 1-to-1 ratio over time. You can see that it's very noisy for our organic rich material. So cutting across a cross-section through this is we can see we do have bank erosion of material and deposition in the center channel for a 3-to-1 organic mixture ratio. But overall, our channel shape is maintained, and there's very little difference along our banks at a 10 through 50-year flood event or upstream crossing. But then downstream, we can see that there's very little change. It stays constant throughout the cross section. And then you can see not having these designs, we have massive bank erosion on both sides and deposition in channel. And for upstream and our downstream is deposition occurring. So this channel is becoming that plain bed form. So comparing this meander bar at a 2%, we're saying, okay, let's look at the organics versus not having organics with that coarse material with slash and root wad. So we can see that just the organics, that very rich organics, we can see here that has less stability than just streambed material. So we say, okay, stream organic should not have a mixture greater than a 1-to-1 ratio. We can see that losing our less organic material ratio, a 3-to-1, is we have a super high channel stability at a 25 and 50-year flood event. And so building this channel just of completely organic material has better stability and maintains a channel shape than having coarse material with our organics. And then at a 3 culvert width spacing, we can see that every design does add stability within inside our, or more stability than just streambed material. You can see that a 1-to-1 ratio of organics, has the most increase in stability for our 25-year flood event. We can say that looking at a 10-year flood event, it is better than having just coarse material and slash. We see that increase for each flood event. So anticipate, if we went to a 75-year flood, are we going to see the same change that we'll see stability increase with the higher flood events? But there's going to be some threshold to where we won't see as much stability. So it'll be interesting to further test, see where does this design start to decrease our stability in our channel. So we cranked our flume up to a 3% slope, and we tested for this was just our original meander bars with coarse material, with root wads, and with slash. And this was all tested at a 1 culvert width spacing. Our prior research proved that anything above a 2% slope shouldn't have a spacing greater than 1 culvert width. So we can see that just coarse material and organics will have greater than a 50% increase in channel stability and almost up to about 68% for a 10-year flood event, looking at coarse material with slash. And we can see that the root wad kind of has better stability once we get above a 10-year flood event, which was very interesting. So we found that to be something we can look at further, but each design will increase channel stability. So looking at our surface elevation plots, again, our top ones are after construction and the bottom graphs are after a 25-year flood event. And we can see that at 3% slope, our channel has become flat, plain bed. So we can look at just adding coarse material as we maintain that channel shape. We do have, you see the elevation starts to increase in the center of the channel. And we start to see some erosion on our banks. We can see this process occur for each design. We start to see it, the slash material, as we see, still has somewhat deep channels, but we still had a little bit of an increase throughout. But diving into that, seeing what's really happening is looking at these different plots. So we can see on our meander bars with just center material, they're completely wiped out with that blue being erosion, and then channel filling up with yellow being deposition. So we can see adding coarse material is we still have that massive deposition occurring in the center of the channel, bank erosion in the blue, and just little changes occurring along our meander bars heads themselves. Once adding the organics in, we can see that we decrease the amount of deposition throughout the whole center of the channel. For root wads, we do have a massive increase around our middle meander bar and downstream. But then adding the slash material is we kind of reduced that deposition throughout the center of the channel. There's a little bit of hot spots. We do get a little more erosion along this bank in between our left bank features. So cutting cross-sectional view through our Streambed material and then our slash material, we can see during our just Streambed material, massive bank erosion, channel becoming flat. That's even after a 10-year event, we start to see that center channel kind of build up for each flood event. You can see downstream, it becomes plain bed after a 10-year event. So looking at our upstream with our slash material, we can see that our channel shape is very well maintained. There's very little change. We do see at 25-year flood event, erosion occur, but then it fills back in to almost right to our 10-year event after a 50-year flood event. And then downstream is very little change as well to our channel shape. So this is maintaining our desired channel shape up through a 50-year flood event. So we increased our slope to a 4% slope. And over our previous research, we found out once we get up above this gradient is we had to increase the size of our material. So we already knew that this meander bar with slash was determined to be kind of our best design for our 2 and 3%. So we kept with that design, but we wanted to change the size of the material in the cone. So just our downstream C design 2 is we kept the same material, that D100 to 200. And then for our third design is we increase that size to being particles that are equal to our D200. So we tested this at 1 culvert width. So we can see in this bar graph here showing stability with our 0 axis being our just natural stream bed material. As we can see by keeping our tail material between our D100 and 200 is we have right around 60% increase in channel stability. But once we move that material size up to be equal to the D200, is we lose stability. We still are above 50% at a 10-year event, but then we lose that stability decreases about to 40% at our 25 and 50-year flood event. And we found out by doing why this was happening is looking at these surface plots, we can see that we started seeing these little bumps of elevation increase is because these particles on our meander bar were being unsteady. There's saltation, they'd fall in the channel, and they'd move 1 to 2 particle diameters downstream and then come to rest. So after a 50-year flood event, you see these little bumps right around here. These particles were there in the same spot after a 50-year flood. Looking at kind of where this erosion and deposition is occurring, we can see that we do get deposition in the center of the channel. During our big events, we do see these particles being lost at our meander bar heads, ending up in that center of the channel. Then we can see that we have little change kind of occurring throughout our meander bar. There's a little erosion and deposition. A lot of this deposition here is just our particles kind of just rotating, moving and stacking up on our meander bar heads due to saltation. So we do see a massive deposition occur right here is because we had a lot of movement out of this meander bar head. They just fell into the center of the channel, and that's where they maintained through the trials. So understanding what happened to our cross-sectional shape is we pulled another cross sections of our just stream bed material and then our design with just our D100 to 200 particles. As we can see, this in our stream bed material comes plain bed, flat, bank erosion, deposition, and center of the channel. But then adding these designs, as we see erosion throughout the channel, a little bit of deposition. There's very little change after that 10-year event. And we can see that for both our upstream and downstream cross sections. So the conclusion of this research study was meander bars with coarse material reduce sediment transport and increase channel stability. Organic material increases channel stability. So we had coarse material worked great, but even adding just the organic material, just a little bit of slash upstream or that root wad, increase that channel stability. And coarse material with slash was the best design that had the highest increase in our channel stability. Organic streambed mixtures, organic mixture at a 1-to-1 ratio or less increases channel stability. And so our recommendations is for a 2% meander bar with slash at a spacing at 2 to 3 culvert widths should be used. If you go up to a 3% slope, meander bars with slash is a design that should be used. And a 4% slope is we keep that same design of meander bars, keeping our tail material between the D100 and 200. And so we found out using that tail material to be equal or greater than D100 is needed to keep that stability through the channel and have that meander bar function as intended. And then organic streambed mixture, a 3-to-1 volume ratio is a great option. It kickstarts the organic or macroinvertebrate life inside the channel already. So it brings in food for fish and other biotas, and it'll help increase bank stability. With that, does any questions?
First off, sorry. Okay, cool. Sorry. First off, just wanted to thank Tyler for the presentation. This was really wonderful and insightful. So yeah, please feel free to put your questions in the chat or raise your hand using the raise command, but I can also start us off with some questions that I've thought of while the presentation's been going on. So one of my questions was, do you think the organic mix of the stream bed is more stable at 25 and 50 year flows due to the saturation or organics, like reducing the buoyancy factor? Sorry, can you even hear what I'm saying? Are you able to just turn? Do you want me to type the question?
No, I heard it.
Okay, great.
Yeah. Yeah. So yeah, that's interesting. I think why we're seeing it is because it's becoming packed. And there's so less, you're getting that stability from the sediment. So we're not seeing much being lost. Throughout our whole 20-foot study section, we probably collected 5 gallons, maybe 10 gallons of organic material with that design that just was transported downstream, which when you increase that more, that volume grew. So I think it's just being able to be weighted down over time. So we're worried about that our material being dried if this is going to float away. So we did mix it in, we wetted it, and then we let it sit for a while. Then a few times to make sure, it'd be soaked. It wasn't just going to float away. But we tested the whole study. We had, especially organics, there was probably 12 designs. So all the stuff was in the stream bed for a couple of 4 months being put through water 5 days a week. So the buoyancy, I don't think, really played a factor after a while.
I have a question, Tyler. When you were comparing areas of erosion versus deposition, were you finding that were you finding that areas that got scoured out or eroded, that material just deposited within your study area elsewhere? And so there was kind of like a net zero within your reach, or did you see that material got pushed downstream out of your flume? So yeah, does that make sense?
Yeah. Yep. Let's see if I can get back to it. Yeah, so let's get to our 2%. We did. So we'd see a lot of our material, like if we're losing it down here, we'd see it start to build up around. So I was just out in the field at Duffner. And so in the lab, we'd see kind of a fine sand belt being built just downstream of our meander bars. And so we get a little scour hole that occurred, and then it all deposited. Most of it was just downstream above our next feature. And this is the same process that we saw in the real world. So it's neat kind of seeing that process happen in the lab, but then also in the field is we did get that banky erosion in between, but we're also seeing that deposit of material right here. So we can see we lost it. We're getting some of that deposit right here, then also just downstream.
Question from the comments. Was the sediment gradation scaled down similar to how flows of channel geometry were scaled down?
Yeah, so everything was scaled by length. So our D50 was our main source. So that had a factor of 7.6. That 7.6 was also scaled to the flow. So actually the flow, I think, was a scale factor of like 400 and something. So we did all that by length. So yes.
I have a few more questions, but I feel like the echoing's bad, so I'm just gonna go over. Oh, Patty has a question.
I missed the beginning of the talk, so you may have talked about this and I just didn't catch it, but I was wondering about the kind of the nature of the organic material, and if you looked at whether the impact that would have on kind of the channel bed structure, the interstitial spaces where bugs like to hide and things like that.
Yeah, so we used dowels to represent our woody feature. Our previous study, we had some people bring some live organics into the flume. We had big algae outbreak, so we spent too much trying to clean that. So we went with trying to, we'll just simulate stream. So we had, smooth, straight dowels. So I think having more of that natural organic material will increase the roughness, increase stability more to add little voids for invertebrates to live. So I think we should see an increase in these values from the field.
Okay, so this was like surface organic material, not kind of mixed in, not integrated into the bed or anything.
No, so our organic streaming mixture was in the bed. So that bed was completely comprised of organics, the full depth of our flume. With our meander bar features of just adding slash above is buried half its depth into the stream bed surface.
Okay, so that's, I was wondering about the kind of the bed behavior. If you have finer, kind of stickier materials that don't have as much structure to them as say gravel, what the characteristics of how the characteristics of the bed might change and be usable by aquatic species.
Yeah, so we saw around our slash material just upstream, we saw fines that were getting deposited around our features, which is very interesting. So I think a bunch of habitat will be created, how we stacked them, interweaved them to kind of make, something at slower velocities that aquatics can just kind of hang out in that zone. And I think we'll see that in the field with being, having more big branches, or that area would increase that.
Okay. We have another question.
I have one more question.
Go, Amiana.
Okay, so this is kind of getting into the more like working with the various agencies like WDFW sort of thing. So if you don't have an answer, Tyler, that's okay. But one thing that we're running up against with a couple of our current sites right now is if we're going to be pursuing a stream bed simulation design, then we're not really allowed to put in anything above the measured D100 out in the field. So like saying, hey, we want to put in a D200 would probably get a lot of pushback from some fish biologists at WDFW. So all these combinations and permutations of slopes and organic stream bed mixture, etc., how would you approach designing a stream bed head to, or stream bed, mandbar to be within that D100 or lower range, but also kind of mixing in this organic material?
Yeah, so
particularly at the steeper slopes, like 4% or so.
Yeah, the particle needs to be considered stable for a flood event. So if you're at like a big 4%, we didn't calculate stability, but you need to calculate it probably even greater than a D100 or not D100, sorry, 100-year flood event, or maybe go up to a 500 and say, okay, this is when the particle is stable and moving. Really communicate the function of the design is, yeah, they are kind of hardened, but they are to maintain a channel shape throughout the structure and keep them away from the walls and keep them more that meandering channel. So that I know there's been pushback with, there's larger stuff in the head is great, but then the tail is also very important because that's kind of holding that head material together. So that also needs to be stable for a certain flood event. We showed that, yeah, you're using stream bed material, but that stream bed material will just wipe away. And here was that a 25-year flood event. So you need to get those stable. So that you start with like a D100 and say, okay, it's stable for a D100. This is what it's going to be. I think there's be a lot of examples in the field that saying, okay, they use, say, the D84, and there's only 40% of the volume was the D84, the rest was smaller. They're being washed out and saying, okay, here's this example of them failing with this size material, but then grab another site that's in the same slope and range and say these were built to have stability in both the head and tail, and they're actually performing as designed. I think grabbing some of those examples and coming through with co-measure and say, okay, this is what happens when you don't have stability for your tail, and here's what happens when you do, and this is the outcomes we want to see, or you're going to come back and fix it later on.
Makes sense. Thanks.
Are there any other questions? Okay. Wait, maybe? No. Okay, I have a couple more questions. Over the lifetime of bed design with organics, do you predict that like the decomp of the organics will impact the implementation of design in like sediment starved systems, anticipating that like transport will be an issue over time if the organics leave?
Yeah, so that is a good question. So over time, we'll see particles degrade. We'll see settling in the bed, but organic or macroinvertebrate stuff will bring in and help build up those void spaces. So you'll see a little settling within that structure, and stability should already be there. So it's kind of a give and take. We'll see some instability go down, but you're also having those environments already kick-started. But yeah, for a starved system, that definitely comes into play of what's upstream and downstream, especially looking with organic mixtures. If there's a small culvert downstream, okay, if we're going to lose, how much material is that going to cause clogging of the culvert downstream? Vice versa, or upstream, is we have massive sediment flux coming in. How much is this going to deposit inside our structure and become plain bed that way? So there's also a bunch of different views you got to take to kind of guide the decision of what should we use. Should we use organics? If we do use organics, we just put it in the bank and leave it without the bed of our setup or bed of our channel. So we still don't limit that development of pools and throughout our system. So that's kind of one thing looking at doing is just make bank stability, but then leave that sediment channel naturally form itself.
Cool. Okay, sorry. One last question. And of course it disappeared. Oh, okay. I was just kind of curious about like how if D200 is anticipated to be stable based on like designing it for like regular sediment stability, how do we see them then become mobile in the system at higher flows if they're supposed to be designed to be stable at over 100-year flow?
Yeah. So I think you'll see them mobile. So if you have a system that has massive erosion, there was one project that had massive bed erosion and kind of the mandrobar kind of fell in and kind of moved downstream. I think they'll be, one time would be mobile. There's really probably maybe a few particle diameters downstream. They'll come to rest. Like a big one that I see was a landing strip. They had super big coarse mandrobar heads, and it got wiped out. But those big boulders, you can still find it in the structure, and they're kind of just separated, maybe moved 2-3 particle diameters, and they're still there to rest. So I don't think they'll be all washed out throughout the whole system. They'll just become set, almost like a rock garden if it does get wiped out.
Cool. Awesome. Okay. Any other questions? Abby, do you have any questions? Okay. All right. Well, then I guess we can go ahead and end a little bit early. Again, thank you so much for presenting, Tyler. It's been a pleasure having you, and I hope everybody has gotten a lot of good information out of this because this is really exciting stuff. And again, we'll be back in next month watching a new presentation, third Thursday of the month at noon. You can catch us virtually this upcoming month. Yeah, thank you. Have a great day, everybody.
Thank you.
Thank you.
Thanks, Tyler.